Hey, chemistry. So I left you last time thinking about this thought experiment. What if I took a piece of iodine, I2 molecules, and I dropped them into a cup that contained both oil and water? What would you see happen? How would that intermolecular forces affect that iodine? So first, let's start by what would happen if I mixed oil and water, so we can get down to the basics of this overall interaction. So if I were to drop oil and water and mix them together, what would happen? Well, they would separate because water is polar, there's dipole-dipole interactions there, and oil is nonpolar, and those are weaker dispersion forces. And the interaction between water molecules with each other is far greater than the interaction between water and oil, so the water molecules will be attracted to each other and essentially kick the oil out, so they will separate. Now, if I were to take this crystal of iodine, this I2 molecule, and I were to drop it into this oil-water mixture, what would we see happen? What kinds of intermolecular forces exist between the iodine in the oil and the iodine in the water? Will the iodine dissolve into either of them? Into both of them? What will we see? And I want you to use intermolecular forces when you think about this. So let's take a look at iodine in a little more detail. So here's the I2 molecule. It is I bonded to another I in a single covalent bond. Is this a polar molecule or a nonpolar molecule? Well, since anything bonded to itself is nonpolar, and all the bonds are nonpolar, this is going to be a nonpolar molecule. So it is not going to be able to interact with water as a dipole-dipole or an ion dipole. It's going to have to interact with an induced dipole situation. But these are highly electronegative atoms. So unlike the oil molecule that contains carbon and hydrogen that are not highly electronegative and therefore has extremely small dipole-induced dipole interactions with water such that they basically separate and don't interact at all, iodine is pretty electronegative, and so there is going to be some of this dipole-induced dipole interaction. If we go to that idea of like dissolves like, iodine is going to dissolve a lot more into nonpolar substances than into polar substances. So when we drop our iodine particle into the water, the iodine crystal, and on its way down, it will go through a layer of oil, which is nonpolar. And because like dissolves like, basically the iodine is going to dissolve fairly readily into the oil, and it's going to turn it purple, which is the color that iodine is when it's not super concentrated into a crystal. It's going to spread out and move evenly. It's not that oil and iodine are really attracted to each other. They're not. It's just that there's really nothing holding the iodine molecules together anymore, and they're free to kind of just spread out over a much larger area. As the iodine drops into the water, it begins interacting with a polar substance, and you end up getting a dipole-induced dipole interaction. The dipole-induced dipole interaction is pretty weak, and so the iodine particles are going to stay together, and only very small amounts are able to dissolve into it. You'll be able to see a little bit of iodine dissolving as it essentially is going to dissolve a small quantity, and that will discolor the water kind of a yellowish in color, but basically most of the iodine is simply just going to drop to the bottom and sit there, and you're going to have very little in the water. How would changing the temperature change this pattern? Would things dissolve more rapidly? Would they dissolve less rapidly? What does changing the temperature do to the rate and the amount at which things can dissolve into solution? So here's a graph looking at the average kinetic energy. Another way of thinking about it is how quickly are those molecules moving and how many of them are in that kinetic energy speed. So if you've got something that is a colder temperature, the blue one, you'll notice that more of the molecules are going fairly slowly, and a few are going fast, but not very many of them. So you get this tail that drops off quickly. But if you increase the kinetic energy and make it hotter, which is the red, basically they're going to shift over, and you're going to have more and more of these molecules moving faster and faster, and that tail will grow. And so basically you're going to see a situation in which more and more of these molecules have enough kinetic energy to overcome the intermolecular forces and to escape. Now, when we're talking about that tail, even at very cold temperatures, a few of the molecules are moving very rapidly. And so take a look at this. This is showing a variety of molecules moving around in either a liquid or a gas phase, depending on how you want to look at it. And I want you to start by picking one molecule and follow its path. So take a moment, pick it, and follow it. So if you do that, what you're going to find is that at any one instance, some of them are moving very slowly and some of them are moving very rapidly. And in fact, individual molecules can change their speed depending on the collision that they have. So let's pick one, and we're going to follow this guy right here, this red one. Notice it's moving kind of slowly, and then it got hit and it accelerates really rapidly. Then it'll hit something else and slow down. So at any one time, many of them are moving very fast, but a few of them are moving slowly. That's what we talk about with the average kinetic energy, is the average movement of the molecules. And that's what temperature actually tells you. Temperature shows the average kinetic energy if you take all the molecules' speeds at once and take the average of that. The higher the temperature, the faster they are moving on average. And the more likely those molecules can overcome the intermolecular forces that are holding them together and allow them to escape. So let's take a look at iodine. So if we take iodine and we simply heat up those crystals, as you see in this image here, the higher the temperature, the more rapidly the iodine is going to convert from a solid into a gas. And so you can see that purplish gas that's coming off in that animated GIF. So that purplish gas is happening because it's reaching higher and higher temperatures. The molecules are moving more rapidly, overcoming those weak dispersion forces that are holding them together as a solid and allowing them to escape. If you look at iodine dissolved in water, its solubility decreases with temperature. So the higher the temperature, the more and more of those iodine molecules overcome the intermolecular forces, in case dipole-induced dipole forces with the water, and the more of them can escape as a gas, and the less would be dissolved in the water. On the other hand, when we're talking about the iodine interacting with the oil molecules, it's actually going to speed up. Now this isn't iodine, this is just dye dropped in water, but it's a similar idea. The iodine will dissolve more rapidly in the oil and spread out more rapidly and have a higher concentration in the oil at higher temperatures, because as you increase the temperature, the iodine crystals will be vibrating, the atoms in there are going to be vibrating more rapidly, overcome the weak dispersion forces and allow them to spread out throughout the oil more readily.